Question. Show that the function f from the set of real numbers to the set of real numbers lying between -1 to 1 defined by f of x is equal to x upon 1 plus modulus of x, where x belongs to the set of real numbers is 1, 1 and onto. Solution. Given function is. First of all, let us learn about function, 1, 1 function and onto function. Definition of function. A function f from set A to set B is a rule which associates each element x belonging to set A to unique element y belonging to set B. Here, the set A is called as domain and set B is known as codomain. If f of x is equal to y, then y is called image of x and x is called as pre-image of y. 1, 1 function. A function f from set A to set B is said to be 1, 1 if distinct elements of A have distinct images in B. That is, for all x1, x2 belonging to set A. F of x1 is equal to f of x2 implies that x1 is equal to x2, or x1 is not equal to x2 implies that f of x1 is not equal to f of x2. Definition of onto function. A function f from set A to set B is said to be onto if every element of B has a pre-image in A. That is, for every y belonging to the set B, there exists some x belonging to the set A such that f of x is equal to y. Let's prove that the given function is 1, 1. Let x and y be two real numbers. Since x and y both are real numbers, so either both have same signs or opposite signs. Case 1. X and y have opposite signs. Let x be positive and y be negative. Since x and y are of opposite signs, so x is not equal to y. For 1, 1 function, we have to prove that f of x is not equal to f of y. Let f of x be equal to f of y, which implies x upon 1 plus modulus of x is equal to y upon 1 plus modulus of y, which implies x upon 1 plus x is equal to y upon 1 minus y, which implies x into 1 minus y is equal to y into 1 plus x, which implies x minus x into y is equal to y plus x into y, which implies x minus y is equal to 2 into xy. Since x is positive and y is negative, so x is greater than y, which implies x minus y is greater than 0, but 2 into xy is negative, so 2 into xy is not equal to x minus y, which implies f of x is not equal to f of y. So, x is not equal to y implies f of x is not equal to f of y, which implies f is 1, 1 function. Similarly, we can prove that the given function will be 1, 1 when x is negative and y is positive. Case 2. Both x and y have same signs. When x and y both are positive, f of x is equal to f of y, which implies x upon 1 plus modulus of x is equal to y upon 1 plus modulus of y, which implies x upon 1 plus x is equal to y upon 1 plus y, which implies x into 1 plus y is equal to y into 1 plus x, which implies x plus xy is equal to y plus xy, which implies x is equal to y. So, f of x is equal to f of y implies x is equal to y, which implies f is 1, 1 function. Similarly, we can prove that the given function will be 1, 1 when both x and y are negative. Hence, from both cases, we can conclude that the given function f is 1, 1. Now, what do we have to prove? Yes, we have to prove that given function f is onto. Now, let y be any arbitrary element of codomain such that y is equal to f of x for some x. Then, we will show that x belongs to domain, that is, the set of real numbers. Since y belongs to the codomain, so either y is equal to 0 or y belongs to the open interval -1 to 0, or y belongs to the open interval 0 to 1. Case 1. Y is equal to 0. So, y is equal to f of x implies that 0 is equal to x upon 1 plus modulus of x, which implies x is equal to 0, which belongs to the set of real numbers. So, 0 is a pre-image of y is equal to 0. Case 2. Y belongs to the open interval -1 to 0, which implies y is negative and y is equal to x upon 1 plus modulus of x, which implies x upon 1 plus modulus of x is negative, which implies x is negative. Therefore, y is equal to x upon 1 minus x, which implies y into 1 minus x is equal to x, which implies y minus xy is equal to x, which implies y is equal to x plus x into y, which implies y is equal to 1 plus y into x, which implies x is equal to y upon 1 plus y. As y belongs to the open interval -1 to 0, therefore y is not equal to -1, which implies y plus 1 is not equal to 0. Therefore, x is equal to y upon 1 plus y, which belongs to the set of real numbers. Hence, for every y belonging to open interval -1 to 0, there exists an element x is equal to y upon 1 plus y belonging to the set of real numbers such that f of x is equal to y. Case 3. Y belongs to the open interval 0 to 1. Same as case 2, we can prove that for every y belonging to open interval 0 to 1, there exists an element x is equal to y upon 1 minus y belonging to the set of real numbers such that f of x is equal to y. So, by combining the three cases, we can say that for every y belonging to the codomain, there exists some x belonging to the domain, such that f of x is equal to y. Hence, by the definition, function f is onto. Thus, we conclude that function f is both 1, 1 and onto.